Hi everyone, I'm Marcus Högås and I'm a postdoctoral researcher at Stockholm University and the Oscar Klein Center. In this video, I will present some work in progress together with a master's graduate student from India, Soumyadeep Dwivedi. And just to give you some background to this project, when we initiated this project, the main goal was, and it still is, as the title suggests, to analyze the effect of bimetric gravity on the Hubble tension. But as the project has evolved, a very important lesson that we have learned is the importance of data selection, especially with respect to baryon acoustic oscillations, BAO. So an alternative title for this talk would, for example, be this one, Impact of BAO data selection on the Hubble tension, because as we will see, it makes a significant difference for the Hubble tension if one uses ordinary 3D BAO data versus 2D BAO data. Okay, but before we go into that, let me just give you a very brief recap of the Hubble tension. So what is the Hubble tension? Well, as probably most of you know, there are different ways to estimate the Hubble constant h0, that is the expansion rate of the universe. And the problem is that some of these estimates do not agree, right? And the most pronounced discrepancy is between the SHOES team estimate here, which is based on a local distance ladder method, and the Planck satellite data here, observing the cosmic microwave background, the CMB. And as you can see here, there is a very clear discrepancy between these two values. And the first reaction to such a discrepancy is, of course, to suspect systematic errors. But people have been working very hard on this for several years now without being able to alleviate the tension, at least not so far. So an alternative way to try and resolve the tension is to look for alternative expansion histories of the universe, because the Planck estimate for the Hubble constant here actually relies on the expansion history being an ordinary lambda CDM model. So the idea is that a different expansion history leads to a different value for the Hubble constant, and if everything works out, the inferred value of the Hubble constant increases from CMB data, increases to a degree which makes it consistent with the SHOES team estimate. Okay, so that's the option that we will explore in this talk now. And here, to modify the expansion history, we will rely on bimetric gravity. So in short, bimetric gravity is an extension of general relativity, GR, that exhibits two metrics instead of one. Another way to think about it is that in addition to the massless spin-2 field of GR, we also have a massive spin-2 field. So at the level of gravitational waves, that means that there are two different types of gravitational wave modes. One massless, as in GR, but also one massive. And these two modes are interacting with each other, which can lead to some very interesting phenomenology, but that's another talk. Let me also mention some of the virtues of bimetric gravity. So one interesting feature is that it can account for the accelerated expansion of the universe without having to introduce a cosmological constant. Here instead, the accelerated expansion is due to the interaction between the two metrics. And these cosmologies are referred to as self-accelerating cosmologies. Another thing that should be mentioned is that the theory is observationally viable. For example, with respect to cosmological observations, gravitational wave observations, local tests of gravity, etc. And the final thing that I would like to mention is that the theory is scientifically appealing in the sense that even the most general version of the theory only introduces 4 additional theory parameters, that is, in addition to the cosmological constant and the gravitational constant they already have in GR. And these theory parameters, they are constants and they can be constrained observationally. And this is different from many other modified gravity theories where you in principle have an infinite number of additional degrees of freedom, which can make it difficult to constrain observationally. But that's not the case in bimetric gravity. All right, so here we are presented with a promising candidate for a modified theory of gravity. So what we'd like to do now is to analyze its effects on the Hubble tension. And to do so, let's have a quick look at the Friedmann equation of this theory. And as you can see here, the Friedmann equation takes the same form as usual. So on the left-hand side here, we have the Hubble parameter as a function of redshift. And on the right-hand side, we have 2 terms. We have the matter energy density and the radiation energy density. So the difference here resides in the last term on the right-hand side here, which I call omega dE, dE for dark energy. And this term, it appears as a result of the interaction between the 2 metrics. So it's a purely bimetric term. And yeah, I will not show you the mathematical form of this term here, which is slightly involved, but we can simply note that it gives an accelerating contribution to the expansion of the universe. So hence the name dark energy. Now let's confront the theory with cosmological data. So here we'll use the CMB compressed likelihood from the last Planck satellite data release. For type 1a supernovae SN1A, we will primarily use the BIND data from the Pantheon dataset as referenced here. But we're also working on implementing the latest Pantheon Plus dataset. Okay. And for BAO data, we will alternate between using 2D BAO as compiled in this reference here versus 3D BAO data from these sources here. But before I show you the results of the data analysis, I'll briefly discuss the differences between 2D BAO data and 3D BAO data. So ordinary 3D BAO data, as we typically use in cosmological data analysis, is based on, for example, counting galaxies and their spatial correlations in some 3-dimensional volume. And these types of observations can, for example, constrain the volume average distance, dV. So as you can see here in this expression, there are 2 factors of the angular diameter distance and 1 factor of radial distance here. So that is pertaining to the 2 angular directions on the sky and the direction along the line of sight. So here it's important to note that in order to infer the radial distance from BAO data, one must assume a fiducial cosmological model. Okay, so in other words, the 3D BAO data, it relies on an assumed background cosmology, which is by default assumed to be a lambda CDM model. 2D BAO data, on the other hand, it only assess the correlations between, for example, galaxies in the angular directions. So that's quantified by this angle here, which is basically the typical angular separation of galaxies on the sky. And the advantage of this way of quantifying BAO data is that it does not rely on any assumed model for the background cosmology. So it means that this data is model independent. And the price you have to pay for this is an increased error budget, with the error increasing from roughly 1% in ordinary 3D BAO data to roughly 10% in 2D BAO. And concerning the model dependence in ordinary 3D BAO data, an important question that has been raised in the recent literature is whether this model dependence introduces a bias in the Hubble constant. And as we will see now, at least in bimetric gravity, the answer seems to be yes. So let's go to the main result. So let me take some time to explain what's going on in this plot here. So first of all, what we have here are marginalized confidence contours when fitting bimetric cosmology to these different data sets here. On the horizontal axis here, we have the Hubble constant. And on the vertical axis, we have theta here, which is the mixing angle between the massive and massless spin 2 modes in bimetric gravity, or gravitational wave modes if you like. So when the mixing angle is 0, so when we are down here, that means that the massless mode is completely aligned with the physical metric. So, that's the GR limit of this theory. So when we are down here at 0 mixing angle, the theory is identical with GR. Okay, and as the mixing angle increases, we get new gravitational phenomenology, for example, new and different background cosmology. The gray band that you can see here, that is the Hughes team estimate for the Hubble constant, which is 73.0 plus minus 1.0. Okay, if we go to the confidence contours here, and if we start with the green contour here, which is in the background, as you can see, if you look closely, it is the 99% credence region when you fit bimetric cosmology to supernovae and CMB. And as you can see here, it spans a very wide range. So that means, that H0 is only weakly constrained by these two data sets in combination. The next contour here is the red one. So that's what you get if you also impose BAO data. And here BAO is ordinary 3D BAO. And if you recall that this here, that is the value for the Hubble constant that you get if you assume an ordinary lambda CDM model. You can see that in bimetric gravity with these data sets, we get a slightly bigger value for the Hubble constant. So it's easing the Hubble tension to some degree, but not fully, right? Finally, the blue contour here, that is what you get if you replace ordinary 3D BAO with 2D BAO. So that is referred to as BAO transverse here, okay? And as you can see, this results in a significant shift in the Hubble constant from lower values here to higher values. And in fact, as you can see, with 2D BAO, the inferred value of H0 is more or less spot on the Hughes team estimate. So in this case, there is actually no tension between the inverse distance ladder and Hughes. So one of the main conclusions that we can draw from this is that the choice of BAO dataset can have a significant impact on the inferred value of the Hubble constant. And in fact, as we have shown here in bimetric cosmology, model independent 2D BAO, it yields a fit which is in agreement with the Hughes team estimate, while the ordinary model dependent 3D BAO results in attention. So this obviously raises the question whether the Hubble tension can be explained by the model dependence in ordinary 3D BAO data in combination with a modified expansion history. So which of the data sets should we use then? 2D BAO or 3D BAO? Well, in the context of a modified expansion history, as here, of course the safest and most conservative choice would be 2D BAO, since it does not assume a lambda CDM cosmology, which is indeed contrary to the kind of cosmology that we are analyzing here, right? So then ideally what we should do now to reach the same 1% accuracy as in ordinary 3D BAO data is to redo the 3D BAO data reduction, assuming a bimetric cosmology rather than a lambda CDM model. But as far as I understand, this is a very challenging task, so I would be very happy to discuss this further with you when we meet. And I should also mention that we are currently in the process of implementing the full unbinned Pantheon Plus dataset. And our preliminary result suggests that it also makes a difference whether one uses the old binned Pantheon data sample or if one uses Pantheon Plus. But hopefully I will have an update ready when we meet. Okay. Right, so I'll stop here and look forward to seeing you later.